All right, so number one, make sure you're here on time, because I always give quizzes right at the beginning. So usually if you're late or something, I'll give you like one free makeup quiz, but that's it. I'm not going to continue because you're continually late. I continually give you makeup quizzes. So number one. Second, these came directly from the homework, so hopefully they look somewhat familiar. Let's crank them out. I'm just going to give you answers here. So this one right here is a chain rule. Outer layer is the sine, so I start there. Derivative of sine is cosine. I rewrite the argument without taking the derivative. Then I multiply times the derivative of what's inside, but that's a product, so I have to do a product rule. So big parentheses here, must be in parentheses. Derivative of the first one is 1 times the second one, and then plus the derivative of the second one, which is negative sine x, and then times the first one x. There you go. That's what I'm looking for right there. Now, you could have cleaned it up a little bit. Up to you. You don't need the 1. You could have made this a minus, but that's the main idea. Okay? Second one is, well, again, a chain. You have to start with something to the 6th power. So the derivative of that, 6 comes out. All of this to the 5th power. Okay, that takes care of the 6th power. Now you go inside, and what's in here? Quotient, right? So you got to do times the entire ugly quotient rule, right? So it's going to be something over the bottom squared. I know that's the way the rule works. So I do derivative of the top times the bottom minus derivative of the bottom times top. So derivative of the top, 1 times the bottom, x cubed plus 1. And then minus the derivative of the bottom is just 3x squared, and then times the top, which is x. There we go. Yes?
So when I did the quiz, I actually didn't take the derivative, but I just left it as like x with the prime sign and didn't actually do 1.
Okay. I'll have to look at it. Yeah. I mean, if you didn't take the derivative, then it's not technically finished, right? Right? Because you could say, all right, you know, you could say, all right, my answer is the derivative of that. Well, you haven't taken a derivative, right? So you still have to actually take the derivatives. Okay. You have a test on Tuesday, right? I sent out a review. All right, so maybe we'll stop 10 minutes early, 15 minutes, and we can talk a little bit about the test. But I want to continue what we were doing last time. Y'all have any questions over anything? How many of you feel like y'all did okay on that quiz? Yeah? Okay. All right, so last time we were talking about implicit differentiation, right? Implicit differentiation. I'm just going to put implicit diff, okay? And the idea, again, was that some equations cannot be solved for y, or for whatever variable you're interested in. And so is there a way to differentiate those equations? And we said, yes, there is, right? And we started to work with the technique. So I want to do some more examples, and let's just see how far we get with this, all right? So let's start out basic, because it's been a whole, 48 hours? So let's go and let's do this. If I give you x cubed plus y to the 4th plus x cubed y to the 4th equals 1. This is an example of an implicit equation, because nobody here wants to go try and solve. Actually, solving for y would actually be easy here. Let me change this. Let me change this to y cubed. That'll make it a little bit harder. Solving for y here, now that I've changed it, will be hard, all right? So we still would like to see, can we find, let me put it, I don't want to put it underneath because that's where I'm going to work. I'm going to say here, find dy dx, which means I want to know the slope of the tangent line, right? That's what I want to know. I want to know how fast I want to know how fast this is. This is basically saying how much does y change if I change x by a small amount. Okay, small meaning like really, really small. Graphically, whatever this curve looks like, we're saying if we start at one point, if I were to change x a little bit, right, make a little bit of a change in x, we call this the dx. Then the question is, it's going to go up, right? If you go over, you're going to have to go up a little bit to get to another point. And what we're trying to find is the ratio of that divided by that. That ratio is rise over run. That gives you the slope of the line, right? I just don't want us to lose sight of the fact that dy dx really just gives us the slope, right, of the tangent. So, anyone remember how I'm going to start this? Other way around, d over dx, both sides of the equation. Exactly. So, is there a question?
So you always started off with d over dx?
Well, okay, so I was going to ask the next question, why are we doing d over dx? Why not d over dy or something like that? Like, why is it that way? Yeah, see, you always have to look at what variable is down here. That variable down there is the one that dictates why you do d over dx. See, that's why I wanted to write this down. Whatever the numerator is, we're figuring out how much that changes, all right? If I just like move the x a little bit, we want to know, you know, the y is going to come up. We want to know that ratio. It is possible that I could have reversed that and I could have put dx over dy. And then I'm asking if I change y, how much does x change by, and then make that ratio. It's not the same answer. And we're going to do that. That's why we want to make sure that we understand this notation. All right, so starting out, what I do, I start. It's kind of like, you know, you've done this for a lot of your mathematical life. You have an equation, and you're going to do something to both sides of the equation, right? You're going to do something on both sides. What we're doing, though, isn't, we're not like, are you okay with her? I'm trying not to be in your way, but I'm just so used to writing a certain way. So what we're doing is we're not like multiplying both sides by a number or adding or subtracting. What we're doing is we're differentiating both sides of the equation. What we do on one side, we do to the other. We're taking the derivative with respect to x over here, and then over here, we're taking the derivative with respect to x also, and that's just 1. Now I look at this, and I see that when I differentiate this over here, I have pluses right here, right? So that means I can differentiate each of these individually, right? So I'm going to write now the derivative with respect to x of x cubed plus now the derivative with respect to x of y to the fourth. Y'all hear what I'm saying? The derivative with respect to x, that's what that statement right there. The derivative with respect to x of x cubed y cubed, and then equals, well, the right side, can we just do that right now? What's the derivative of a constant? 0 all the time. So this is going to be 0. Questions there? That's just setting up. We haven't taken any derivatives other than the constant. We did that one. Now, this is where things get tricky, all right? If you're differentiating with respect to x, and the variable in here is just x's, then you're going to do the derivative the way that we started this whole thing. The answer to this should just be 3x squared, right? But technically, what we're doing is we're doing the power rule, right? 3 is coming down. X to the second power, we reduce the power by 1. But then the chain rule says, now I have to take the derivative of the base, right, of this. With respect to what? With respect to x, right? So it looks like this. I'm taking the derivative with respect to x of that x that I just showed you right here. And that turns into essentially dx over dx, right? It's almost like you're sliding the x up top, like a fraction. And then dx over dx will turn into a 1. So this, at the end of the day, will turn out to be 3x squared. But the idea is important, especially for the next one, right? Because here, we're differentiating with respect to x, but we're differentiating something that does not have x and it has y. So I have to first start with the power rule, right? So what do I get first? 4y cubed. But then chain rule says now you must take the derivative of what's here, right? With respect to x, right? So the derivative with respect to x of what? Of y, right? Of y. Maybe I could have put this in parentheses to be consistent here. That still turns out to be a 1. But see, does this turn out to be 1? No. Why is this 1? They're the same, right? I'm saying here what I'm saying, look at this right here is this statement right here. I'm saying, how much does x change, right? If I change x by a small amount. Well, that ratio should be 1, right? Because you're saying if I move by x, how much did x change by? Well, by that same amount, and you divide the two, you get 1. Or you just look at it like a fraction. 4 divided by 4 is 1. But this does not say the same thing. But this, in fact, is actually what we're looking for, isn't it? dy dx is actually what I'm asking you to find. So the fact that it is appearing in this is actually a great thing. If this never appears, then how are you going to solve for it, right? Okay, I'm going to continue. Plus, okay, over here, I'm taking derivative with respect to x, but I have two variables here, don't I? I have x and y, and they're being multiplied, which means I must apply the product rule when I differentiate this. So let me set that up. It'll be, well, how do we do product again? It's the derivative of the first one, right? So I'm going to take the derivative with respect to x of the first one, right? But then times what? G, which would be for us what? Y cubed. And then plus, this is product rule. Now the derivative of the second one, or g, which would be, I'm going to write it down, the derivative with respect to x of the second one is y cubed, right? So now I'm taking derivative of that one, which I haven't done, right? I haven't taken the derivative. I'm just writing down what I'm going to do. And then what? Times what? X cubed. Good. And don't forget, we still have equals 0 over here. So does everyone see this product rule on this? Any questions there? I'm going to move up because I know it's hard to see that down there. So now let me write the next line. This just becomes 3x squared times 1, so I don't need to write the 1, plus, okay, 4y cubed times, I'm not going to write it that way anymore, I'm going to write it dy dx. So I'm going to put those together into like a fraction. And then plus, okay. Y'all are too quiet for me. Emily's not here, right? Emily? No? All right, Lewis? Where's Lewis? There you are. Okay, Lewis. Are you following this? Like, you feel like you're getting it? Yes? Okay. So can you give me what this becomes? 3x to the power of 2. Okay.
And then it would be
dx over dx, which would turn into 1, right? I'm going to write it, though, okay? So next part would be I'm supposed to take the derivative with respect to x of x, right? So that's good. Now what, Lewis? Times y to the third power. Do you want to keep going or no?
Yeah.
Okay. So Lewis, tell me how you're going to write this. What's derivative of this? 3y to the power of 2 times dy dx. So I'm going to write it again as I'm taking derivative with respect to x of y. That's the chain rule, which just turns into dy dx. You don't have to, look, once you get comfortable with this, you don't need to be writing this. You could just say that that was 3x squared, be done. You could say that this is going to be 3y squared dy dx. That's fine. Okay, let's see. We're not done there, right? Almost. Times x cubed equals 0. Good. Anybody have questions? No? Yes?
So did you work out the quotient rule for x cubed times x or y cubed?
X cubed.
The last term for.
I did the product rule. Product rule, yes. I did that right. The product rule was done. Where is it? Right here. This is where I did the product rule. And this is actually the product rule right there. This is, if you want to look at this as being the f function and the g function, this was f prime right there times g plus this was g prime and then this was f. Do you see that? Is that what you're asking me? Okay, so we're good or? Okay. All right, everyone good? Okay, let me just clean up a little bit more. This is 3x squared plus 4y cubed times dy dx. Okay, plus this is just 3x squared because that becomes 1 times y cubed plus, okay, this I'm going to write as 3y squared times dy dx. I put those together, and then times x cubed equals 0. That is all we did last class, right? Like we did a couple of examples, and this is where I stopped. But we're actually not done, because what did the problem ask us to do? Find dy dx, right? Now we have dy dx in this equation, but we have not solved for dy dx yet. We need to try and get dy dx by itself on one side of the equation. Like, you know, dy dx equals something. So this is where you have to start breaking out your algebra, all right? And we're just going to do some algebraic manipulations to try and isolate the dy dx. So what I do first, and what you should do as well, is first identify the terms that have dy dx in them. I have this term has dy dx, and this term right here has dy dx, right? None of the others have dy dx. So my first step is going to make sure I get every dy dx term on one side of the equation. Everything that does not have dy dx, I'm going to get to the other side of the equation. And fortunately for me, these are both on the left, right? So I'm going to leave these here. I'm going to move these to the other side, right? So I move those to the other side. And all I have to do that is change their signs, right? Like if I want to take that to the other side, it becomes negative. Take that to the other side, because it's positive, it becomes negative on the other side as well. So I'm going to have this. Negative 3x squared minus 3x squared y cubed. Questions there? It's just algebra, right? Moving things around. We good? We good? Yes, yes? Why do you think I did that? Is there a question? Yes. What did I put? Where?
I forgot the x cubed.
Where did I forget? Oh, at the very end of this one. Thank you. Yes, right here. That right there. I said, thank you. I could see the look on your face, and then I knew something was wrong. I forgot the x cubed here. I underlined the whole thing, but when I wrote it down, I didn't write the whole thing. Yes? Okay. Why do you think I did that? Why did I get things that have dy dx here and things that didn't over there? What do you think my next step is?
You combine them.
Well, if they were exactly like terms, they would have to have the exact same variables to the exact same powers. What are we trying to do? Solve for dy dx, right? So I'm trying to get it by itself. Is there any way you can kind of like factor it, right? Do these both have dy dx in them? So do it like a GCF. Don't do a total greatest common factor, but just pull out the dy dx from both of those. So factor dy dx out of the left side. If I do that, what would still be here, right? If I pull the dy dx here and pull the dy dx here out, I'll still have the 4y cubed, right? Plus, and then I'll have the 3y squared and then the x cubed that I'd forgotten to put there a second ago. And that equals the other side. With me? One more step. I want this by itself, which means I don't want this here, right? And it's being multiplied. It's this times this. So how do we undo multiplication? Or how do we get rid of something on one side of the equation if it's being multiplied? We divide, right? So I'm going to divide both sides of the equation by that big ugly thing. And don't freak out because you're not going to have to do any more after this. You divide this side by that, and you'll be done. And we get a final answer. I'm going to put the answer over here. It may not show up on camera, but we have dy dx equals negative 3x squared minus 3x squared y cubed over 4y cubed plus 3y squared x cubed. There is some more algebra we could do there, okay? There is some more, but we've got dy dx by itself. Questions? What I'm going to do now is I'm going to graph the original equation. And I need your help because I erased it.
X cubed
Okay, hold on. X cubed
plus y to the fourth power
plus y to the fourth power
plus x cubed
plus x cubed
y cubed.
times y cubed. Yeah, I changed it back. Equals 1. Okay, there's the graph of this thing. Is the graph you're looking at a function, a traditional function? Is it yes or no? Why? If yes, why? If no, why? No, why? Doesn't pass the vertical line test, right? That does not pass the vertical line test. So if I were to tell you right now, hey, go to this x value right here and give me the slope of the tangent line, you don't know if I'm talking about this point or this point, right? You don't know which one I'm referring to. So that's why our derivative formula requires both the x and the y coordinate. It needs us to specify exactly where we are. So if I gave it the correct x and y coordinate and plugged in, I could get the slope of that tangent line. Make sense? All right. Let's check one place. I think I'm confident that that point lives on the curve. Do you agree that that point lives there? What is that point? Can you tell? What's the x and y coordinate there? 0, 1, right? 0 for x, 1 for y. What does it look like to you the slope of the tangent line is there? Looks like 0? Everyone agree that looks like the slope of the tangent line there would be 0? Well, how do we confirm that? We take this x and this y and we plug it into this formula and see if we get 0. Let's see if we do. So at the point 0, 1, dy dx becomes, okay, if I replace all my x's with zeros, do you all agree that goes away, that entire thing goes away, and that thing goes away, right? So I have, on top I'll have 0, on the bottom I have a 0 on the bottom right, plus, now what about here? Does this go away? What was y? 1, so 1 cubed is 1, 1 times 4 is 4, so we get 4. What's 0 divided by 4? 0, right? That's not undefined. You can't have 0 on the bottom. We can have 0 on top. So 0, right? Which matches what we're seeing visually, right? If I wanted to go to a different point, I would have to know what the point is. Like that's a hard thing to generally get with these, but if I had that point, whatever that x and y was, I'd plug it in here, and that would give me the slope of the tangent line. Okay? All right. Ready for some more? Don't look so excited. So I think what I'm going to do is I'm going to start by showing the graph of this. I'm just going to make it up. All right, here we go. Let's do sine. And inside of sine, what do you say we do? X times y plus y squared. All right. And then next to it, I'm going to put minus. I'm going to try and confuse you. X squared y, and then equals 4 minus 2x plus y. There we go. It's kind of crazy, isn't it? Crazy looking function, or crazy, not function, crazy looking graph, right? And so I would like to be able to find the slopes of tangent lines different places. So you may be sitting there at some point going, you know, like, you probably think this more than I want to know you think it. Like, why the hell are we doing this, right? So think about think about an object in the real world, okay, that is moving along the ground, right? Something that's moving. It could be a car, it could be a missile. Well, I guess a missile's not on the ground, but anything that's moving, right? And we want to try and figure out how fast it's moving and in what sort of direction it's going. So like if we're looking from the top down, let's make this an easy one. Let's say this is a little ant or a little bug. Okay, there's my little bug, and he's walking, right? And I can try and figure out at any point in time that tangent line will actually, in like a physics class, would represent the direction of the object, and then also you can figure out its speed. So that's what the significance of the derivative would be. And what we want is, in the real world, we can't say, hey, you better walk so that when I look at your curve, it better be a function, right? Like I want to have a little more flexibility, where if the bug goes and turns back and goes like that, or turns back, right, that my calculus doesn't fall apart. Because if I require that this thing travel so that when I draw vertical lines, it's a function, then I'm limited, aren't I? Where in the real world, things may do whatever they want to do, and I still want to have a calculus that can work. Does that make sense to you? That's why we're doing this implicit. All right. Let me write this down. Looks terrible. It's sine xy plus y squared minus x squared y equals 4 minus 2x plus y. And my directions to you here are to find dy dx. All right, find dy dx. So here I go. I'm going to differentiate with respect to what? With respect to x. That's the way we say that. So we're going to write d over dx. So d over dx of the left side minus x squared y. That's the left side. And then I'm going to do the derivative with respect to x of the right side. All right, here we go. On the left side, we have a subtraction, so I can do each one, right? On the right side, I have subtraction and addition, so I can do 3 different derivatives there, right? Let me write that out. On the left side, I need to take the derivative with respect to x of the first piece, sine of xy plus y squared. That's going to suck. And then after I do that, notice I have 2 parentheses. One that represents what I'm taking the derivative of, and the other one is closing off the argument of the sine function. So after I do that, I'm going to subtract from that the derivative with respect to x of this product x times y, right? That's a product. So I'm going to put those together, and I'm going to take a derivative. Am I done on the left side? Do I have everything accounted for there? Yes? So equals. And now I had three things over here. I need to take derivative of each one. So the derivative with respect to x of 4, I already know that's going to be 0 because it's a constant, minus the derivative with respect to x of 2x, and then plus the derivative with respect to x of y. Any questions? Did I mess anything up? Everything look good to you? Any volunteers? I'm going to be nice. My volunteers can take any of these derivatives they want. If not, I'll assign it to you. Go ahead. Which one do you want? You wanted to start with this one? You're just jumping right in. Okay. Okay, that's fine. Okay, so tell me what the derivative of this is. Everyone pay attention. This is the most difficult one of the whole thing. So tell me what you're doing.
First, you're going to start on the outside.
Okay.
So sine and cosine.
So derivative of that's cosine. So I write cosine, all right.
Keep the same parentheses.
Keep what's in the parentheses inside there. So keep the argument the same. So you're using chain rule, right? Now what?
And then you're going to multiply by
Multiply by
the derivative of the inside.
do you just want me to write that, or do you want to actually do the derivative?
Do it.
You want to just do it? Okay, so does everyone understand the next thing that's about to happen is we're about to take derivative of this? Yes? Go ahead. I'm going to put parentheses. Is that okay?
Yeah.
I'm going to put a pretty big parenthesis because I know what's about to happen here. Okay, so you have to take derivative of what's inside. Tell me how you're going to do that.
So that's going to be the sum differential.
Sum and difference, so you'll do each one individually. Okay, do that one first. Well, how are you going to do that one?
That's a product.
That's a product rule.
So on
Right.
the left side, we're going to do first the derivative of x.
Yeah, let me do something. So right now, what I write in red is going to be us taking the derivative of that piece right there. That is, you said the derivative with respect to x of x. That will turn into a 1.
And then they'll multiply
By
by y.
y.
And then
Add.
the derivative of g, I guess, which would be just d over dx of y.
D over dx. So when y'all say this d over dx, you can say exactly the way you did, d over dx. Or you can say the derivative with respect to x of y. That's the more mathy way to say it, the derivative with respect to x of y. But you're doing everything's perfect here. Does everyone see the product rule that just happened? Yes? Are you done with product rule? What do you still need?
You have to multiply
By x. So this is your f prime g plus g prime f. There it is. All right, very good. We're still not done, because now we're going to have to do, because this was a plus, we have to take the derivative of this one now, right? Plus, I didn't even make my parentheses big enough. Okay, plus